Hi all, welcome to part 10 of the video lecture on combinational circuits. See, we were discussing different combinational circuits, right? So mainly we gone through the adder circuit and its variation. Now let's see another important combinational circuit that is having lots of application in CPU design and all. So that is something called the magnitude comparator, right? So given two numbers, are you able to compare their magnitude, the actual content, actual value, right? Whether two numbers, whether they are equal or one is greater or other is less, like that. So in programming and all, you know, right, wherever the situation is coming. So it's something very just like addition. It's a very fundamental operation we need, right? So how we can implement it, right, in a typical computer? How we can implement it? Say magnitude comparator is a combination circuit. Magnitude comparator is a combination circuit that compares two numbers, say a and b, and determines their relative magnitude. So which is large, like that, or if both are equal, that accordingly it has to answer. The outcome of the comparison is specified by three binary variables that indicate. So if a greater than b, let me express it by a variable. I can use some new variable, say this is denoted by x. So whenever this x is equal to 1, that what I mean is like a greater than b. Similarly, I can denote it by a variable y. So y is equal to 1 indicates that both are of same magnitude, and let it be denoted by z. So you can use different variable, or simply for the time you can assume a greater than b, let it be a variable that says that the magnitude of the content inside a is greater than that of b, right? So that is it. So how we can do it? So everything is fundamentally represented in the form of zeros and ones, right? So in the form of binary. So that binary comparison you are supposed to do, just like the binary addition and subtraction and multiplication, of course, you done. Can you compare two binary numbers? That is a fundamental question, right? So whether it is in any number system, high level language you are following, but when it comes to machine, everything is in the form of zeros and ones, right? So the straightforward method is the method one, that is using truth table. So what you can do is, just like we done for full adder circuit, half adder circuit and all, so you write the half truth table, and for using the truth table you try to see what are all the situation where this a greater than b is going to give you a 1. Accordingly you can simplify, and you can find out the expression for a greater than b, and you can implement it. Similarly, so write down all combination the truth table and see whether a equal to b or not, like that. So hope you know how to do the truth table method. But you know what is the difficulty we are facing here? As it is in binary, to compare to n bit number, for example the numbers are of some 3 bit numbers, you have to compare. So just this is your tag, whether this 010 is equal to 110, you know they are not equal, and say this is 2, this is 6, so this is larger, so this is a relation. So how a computer can identify this? What it will do, it will depend on the truth table, right? How many entries will be there in the truth table? We don't know what kind of a number is this n. It's just a 3 bit number. So using 3 bits, you know the first number itself can be like 3 bits, like a0, a1, a2. So this can be like a 000 001, right, like that. Similarly for the second one number, the bits are like b2, b1, b0. So the bits can go like so. This is one of the combination. Now see, with this first number to be the 0 itself, second number can be something like this. First number to be 0 itself, second number can be something like this, right? So can you imagine how many combinations are there, how many entries are needed in the truth table? See, for fixing this combination itself, this can go for 8 ways. Similarly, when you take a different combination for this a, this is 001, this b can go for 000, sorry, this is not there, 001 itself b can go like 001 itself b can go like, right? So like that 8 combinations. So for this combination itself some 8 combinations are there. So 8 plus 8 plus 8, so totally 64 combinations are there. Is it clear? So how I am telling you about this, I think you can visualize it. It's not something surprising, but anyways, if somebody is having doubt on it, let me write it clearly. Yeah, fine. Something is happening. One second. So it created 2 copy of it. what I need is a blank page. Yeah. So what I'm saying, like so when I have two numbers, say the first number 3-bit number, say A0 A1 A2, second number is like B0 B1 B2, right? Accordingly I have to compare them. So just like situation, x is a variable denoting a greater than b, say x denotes a greater than b, and y denotes a equal to b, and z denotes a less than b, like that. So the outputs, these are all this. So I have a 3 plus 3 6 input variable, and x y z three output variable, right? So then I'm trying to write the combinations. So see, here I can have a 0 0 0, here I can have a 0 0 0. Now this 0 0 0 itself, here I can go like a 0 0 1, right? 0 0 0 0 1 0. So like that, this 0 0 0 itself is giving me some 8 entries, 8 rows in the truth table. So this is some 8 rows, right? 8. Now again, when I take the next combination for the first number, again the second number can go like this 0 0 1 itself, second number can be like this 0 0 0 sorry, yeah, same combination. Second number can go like 0 1 0, etc. This 0 0 0 1 itself, the second number can go up to this. Now another 8 combination, right? So like that. Now when you take 0 1 0, you will get some 8, right? 8. Then you when you fix this like so, etc., you can go for this a itself, some 8 combination. The last combination is like 1 1 1, and that time again this can go like 0 0 0 2 1 1 1 0 0 0 1, etc. 1 1 1 1 1 1. See, 8 combinations. Totally how many combinations are there? 8 plus 8 plus 8. So like that, 8 into 8, right? So 8 such ways are there for a, and for each such a possibility b can go for 8 ways. So totally 8 into 8, 64 combinations are there. Or so as you know, why I am getting 64 rows in the input, because I have so this is my input, right? So input is actually 6 bits. So how many combinations are possible using 6 bits? 2 raised to 6 equal to 64 rows are there in the truth table. Right, now for each row, now you tell me what is this. These two numbers, first row is saying like both are same, right? So this will be 1 and these two will be 0. Now tell me what about this. Here you can see that. So it's a important observation. See, here you can see that just right now, you know, small numbers only, right? So you know the magnitude. So this is 0 and this is 1. So this b is greater, right? B is greater. So that is the situation, is it, right? B greater than a. And the other two cases are 0. Fine, am I writing correctly? So these two cases are 0 and this corresponds to 1, and similarly here also b, this is, it is 1. Now when you are taking this also, because this is 7, b is 7, a is 0, right? This is a case, right? So here you will get a number of ones, and again this 0 0 0 1, and now this a is greater, right? So this will be 1, these two will be 0. Now both are same, so this will be 0, this will be 1, and this will be 0. Is it clear? So similarly the last case, both are same, so this will be like this. So like that you can fill the table for all the entries, and now you minimize for x. Say just look at the truth table, and what are all the cases where this x is giving me 1. So see, the truth table is now very complex, right? So when you are trying k-map itself, you know how to write the k-map for 5 variable at most, but you can generalize it to 6 or 7 variable. But in practical cases, we don't want such complex function. Why we have to think of a function that is involving this truth table method is not good. That is what I am saying, because 64 combination you have to explore and you have to minimize. So it's very much a tedious task, right? I don't want it. Just for a 3-bit number comparison itself, I need a truth table with 64 rows. So it's a very complex thing, and k-map itself we don't know how to do it at this for the time being, right? So that's a difficulty we are facing. So in general, tell me, suppose 3 bits number, it is actually what happened. Yeah, let's take a new page and write the conclusion. So comparison of two n-bit numbers, I observed that the truth table contains 64 entries, right? sorry, two 3-bit numbers, 64 entries. How I am getting the 64? 64 is actually 2 raised to this 2 into 3, something like this, right? Because 3 plus 3, like that. 2. So because the input is now, yeah, so, yeah, I hope you get it right. How I am getting it, because I have a why it is so, because 6 input bits are there, so that is why you are getting 2 raised to 6 combinations, right? Like that. Now can you generalize it, like what about the comparison of two n bit numbers? Now the comparison of two n bit numbers involves, you can generalize now, right? So n bit number means there will be 2n input bits. So how many combinations are possible using 2n bits? This many rows are there in truth table, right? So that is the conclusion I made, and it's very complex thing, right? So just so for 2 n bit number, there are 2 raised to 2 power n entries in the truth table. So this method will work, but it's become too cumbersome. Yeah, that about it. Now can I have a easy method, some shortcut for doing it, right? So that is where this logics and all you have to apply. So can you do this in a better way without depending on, I mean, the traditional, this is the normal approach we are having, right? So for further full order everywhere we apply this method because it is fine for in that case. But here the number of rows in the truth table is something like 2 power 2 power. So that is the difficulty we are facing. So can we do it in a better way? So this is logic is given here. So how can I explain this? So to explain this, what is the thing, I will take example and I will let you know how things are happening. So this a equal to b is something very straightforward. So it is given by I mean x3 dot a equal to b is, assume that it's a variable, so this is giving me a 1 when both a and b are same. So in that case, see this AND operation, a 4 input AND gate I am having, and the inputs to the 4 input AND gate is like x3 x2 x1 x0, and each xi is something like a XNOR of the bits, and you know, the when the corresponding bits are same, this XNOR operation is going to give me a 1, right? So when all bits are same, all x0 x1 x2 x3 will be 1, and all together this AND operation will give me a 1. So let me take an example. See here, let the first number be let the first number be, so what I am doing is I am yeah, let's take example here, that is safe. Say I'm having two numbers a and b. Number a is like some 4-bit number I'm taking, so let it be my number, and number b is like 1011. So and you know that both are same, so now I need to implement this using some smart logic, right? You know that these two numbers are same, right? So I just want to implement it logically. So first what I'm doing is, without depending on root table and all, I'm just comparing each bit side. If all the bits are same, I can say that this number is equal, I mean the equality satisfies. So when I'm looking at the least significant bit, you can see that this is 1 1, right? So what I'm doing is, I have a variable x0, and the variable x0 is defined like the bit a0 b0 plus a0 complement b0 complement. See, the variable xi is defined like ai bi and ai complement bi complement. So here I am doing like this. So what I am doing is, in this case, this is my bits, right? So the bit, this is bit a0 a1 a2 a3, and similarly here the bits I can write like b1 b2 b3. So that is the case. Now you can see that which condition is true here, because both bits are 1 there, and operation is giving me 1. So here I am getting a 1, here I am getting a 0, so I am getting a 1. So the conclusion is x0 is 1. Similarly, next I can take a x1. So when I am taking x1, I will be taking the next bits, right? This will be a1 b1 plus a1 complement b1 complement, right? So yeah, here also same situation. So this bits are 1 1, so this will be 1 and this will be 0, right? The complement will be 0, so this is 1. X1 is also 1. Now when I'm taking x2, my formulation is like a 2 complement, sorry, a2 b2 plus a2 complement b2 complement, like that. So now you know that a2 b2 is 0 0, right? So it's going to give me a 0, but this will catch because a2 complement is 1, b2 complement is 1, 1 dot 1 is 1, right? So this is also give me a 1. Now finally this x3, when I am observing, same thing, a3 b3 plus a3 complement b3 complement. So this is something very straightforward. I am writing this if for those who are still having doubt, right? So hope it is clear, right? So like that I am getting. Now I am setting the variable. So this is my variable a equal to b. So this is, assume that this is a single variable. Okay, so this is equal to or if you want you can use this equality in two expressions are equal by this notation, something we already know. Fine. So that's up to you. Yeah. So in textbook and all, typically for equality they are using this notation, 3 lines. Fine. And this is equivalent to what? This is equivalent to these variables like x3 dot x2 dot x1 dot x0. So when I am getting, so in this case, you know, all these things are x3 is 1, x2 is 1, x1 is 1, x0 is 1, like that I got, right? So this is giving me a 1. So whenever this variable is evaluating a 1, I can say that this is the case, right? So it's very simple, right? Simply I am comparing all the bits. And can you tell me what is this operation? This xi is equal to ai bi or ai complement bi complement. This is actually your XNOR, like ai. This is the typical notation of XNOR gate. So you can denote like this, or ai, the XOR operation, it's a complement of XOR operation. So either you can use an XOR and a complement bubble at the end, you know the notation, and or you can directly use a XNOR gate if it is available, or you can do implement it with the AND gate, OR gate and NOT gate, like that. So different ways are there. So the XNOR operation, the speciality of XNOR A XNOR B is AB plus A bar B bar, is actually when both inputs are same, this XNOR gate is going to give you a 1. So that is what is needed for me to implement the equality case. So that is fine. So the equality case is fine, right? Now what about whether one number is greater than the other one or not? So this here I have a nice concept that also by observation you can understand why it is true. Some bigger expression is given, but you have to be clear, right? So now the situation is I am exploring some cases where A is greater than B. So let me take an example. Say the number AB, something like 1 0 1 0 0 0, something, you know, right? And B is like I need a smaller number, say 0 1 1 1. You know that this is your 8, right? And this is your 7. So definitely when you compare, this 8 is greater than 7 and this condition has to be 1. So that is a requirement I am having. Now can I implement it using some logic? Same way I am thinking, like this numbers are like this is your A3, A2, A1, A0. So here it is B3, B2, B1, B0. So when I am looking at the most significant bit itself, you can see that the bits are like A3 is 1 and B3 is 0. So this is an indication, right? So definitely this A3, this when you look at two binary numbers, the most significant bit is 1 for one number and most significant bit is 0 for another number. So definitely that another number will be having a smaller value. So that is something straightforward, right? The one with this one will be having a higher value. So how can you capture this situation? This is something corresponds to this A3 is 1 and B3 is 0. 0 or its complement is giving me a 1. Okay? Or complement, either you can use a dash operator or C, something like that. So this is going to evaluate a 1 and this is saying me like this number is greater than this. Now let me take another example. So this is example 1. Now I am taking another two numbers, say A and B. So here I am trying like this is the first number and B is like I am making this bit same. Right now I am seeing how can I get a value smaller than this. See, so to make this happen I need some more adjustment because with 8 this is somewhat difficult. So what I am trying is this more significant bit I am fixing to be same and let it be 9. Okay, now I am making this as 8, so definitely this is your 9 and this is your 8, and you know that now also A is greater than B. Now how can you capture this situation? So that is my question. Now the thing is that this, let it be A0, A1, A2, A3, and here let it be B3, B2, B1, B0. Now you can see that in this case both A3 and B3 are same, right? A3 and B3 are same. Same in the sense, hope you remember, if two bits are same, if their XNOR operation will give me a 1. So that is already captured by X3, right? So this situation is something like X3. X3, hope you remember what is your X3. X3 is A3, B3 plus A3 is same thing, you can reuse, same circuit I am having, right? A3 complement, B3 complement, and in that case both A3, B3 are 1, so this is going to give me a 1. So if bits are same, this X3 the corresponding xi is going to give me a 1, that I know already, so I am just depending. So here I observed that this x3 is found to be 1 in this case, right? Now you can see that the second bit, see, yeah, second bit is also same, right? So that is the case. So how can I write it? So x2 is also giving me a 1 because those two bits are same. Now these two bits are same, so that means this x1 is also giving me a 1. Now finally here I have the magic, right? So not like magic. So what is happening? So this is going to say here these three bits are found to be same, right? And the only difference is happening at the last bit, and that bit is going to determine which is larger. And here also, as these bits are same, the last bit, if it is 1, that is a greater number, if it is 0, otherwise, right? So this 1 is making this a bigger in this case also. So that is something I can write like for the last bit, it is like a0, right? A0 is 1 and B0 is 0, something like this. So this expression is giving me a 1 in this case, and that is saying me like this number is bigger. Let me take one more example for clarity and so that you can conclude by yourself. So let I am taking few more bits, like let the first number be say 1010. You know what is this number, and let me make this be like 1000. 1, fine. So you know this is your 10 and this is your 9, definitely this a is greater. Now what is the case here? What is happening here? Here you can see these bits, same way I am labeling the bits. See here B3, B2, B1, B0, and finally you can see that here also x3 is 1, saying that these first two bits are same, and I am getting x2 also same. So that is the situation. See here the difference is happening at so first two bits are same. Now the change is happening at the third bit, and that third bit itself, for A it is 1 and for B it is 0. Or I can write it like this is my A1, bit A1, right? A1 and B1 complement, something like this. Now can you tell me the fourth case? Can you have a example like, so what I need a change at the second position. All other things I explored, right? So let the numbers be 1100, and let this number be, see this is not going to make an example for me, 1100, fine. This is your 13 and this is your 12, and you know that this 13 is greater than 12, fine. I'm just creating example because I know the method, accordingly I'm creating. Now you also you can also create, right? So yeah, A1, A0. Similarly here it is B3, B2, B1, B0. So what I can conclude here, what is happening, x3 is 1. See this example is just like this one, right? So I don't want it, I just want to change in the second position. Let me erase it, sorry for it. What I need is, I need a change in the second position. Yeah, same number let me take, and B let me take like 1001, fine. This is your 12 and this is your 9, and yeah, same way, sorry for the delay. A3, A2, A1, A0. Here it is B3, B2, B1, B0, and I can see that this x3 is 1, and yeah, next bit is having the change for the first time, and you can see this A3, this is A2. A2 is 1 and B2 is 0, or B2 complement is 1. So this is the case. So altogether, how can I write an expression that is going to check whether A is greater than B? So first thing is the look at the more significant bit. If both more significant bits are same, I have to check the second bit. If more significant bit are different, and if this is true, I am done. So this is first case. So this is capture. So this first case is an example for this, right? So if that is the case, more significant bits are different, and for A it is 1 and for B it is 0. So fine. Now the second case is like the more significant bit is same, but the second bit is having a different. That is, more significant bit is same is captured by x3, and the second bit is different means this A2 B2 complement is going to give me a 1. So this case fine. Now the fourth case. Now the third case is like the more significant bit is same and the second bit is also same. Now I have a change in the next bit, and that also like the A1 is 1 and B1 is 0, something like this third case, right? Now the last thing is the first bit is more significant bit is same, second bit second MSB is same, and next one is also same, but in the last position I have the change, and that is like A0 B0 complement. I mean this case, if any one of this case has satisfies also, because I have a 4-bit number comparison, only 4 cases I can have, right? So I'm just observing each and every bit. I can say clearly that A is greater than B. Now can you tell me what is the expression for B greater than A? So this is straightforward for you. So let me write. So A greater than B is going to give me a 1 in cases like if I have a 4-bit comparison, I am assuming, otherwise you have to generalize it, you know it, right? So this is something like A3 is 1 and B3 is 0, or both are same and A2 is 1, B2 is 0, or first bits are same, I mean MSB same, next set is also same. Now change is happening in A1 position, A1 B1 complement, or the last case is like x3 x2 x1 a0 b0 complement. Fine. Now what is the case that A less than B? Now it is very straightforward, the opposite thing should happen, right? So it's like when you look at the most significant bit, for A it has to be 0 and for B it has to be 1. So this is one case, or both are same and for it has to A it has to be the next bit change is happening, and for A it is 0 and for B it is 1, or first 2 bits are same, that is x3 and x2, and for A it is 0 and for B it is 1, or the last case first 3 bits are same and for last position for A it is 0 and for B it is 1. Clear? So this is for 4-bit number comparisons. Same thing you can generalize for any number of bits. So this is what is written here. You may be surprised to see this expression, but it's very simple one, right? Yeah. So that about it. So this is what is capturing A, both are same, and these two things are capturing the inequalities like A greater than B and B greater than A. Yeah, I explained very clearly with a proper example. Now what about the circuit implementation? If you see the expression like this, and if you try to implement using XNOR and or everything, it may be something complex. You can implement, no problem, but you will get a very confusing example. But in the exam and all, they can ask you like, and also in the next semester, you are supposed to implement all these circuits you studied here, and that time also for implementation, if you make it very complex, you may not get the output, right? So always try to draw the circuit. So drawing the circuit is also an art, and that you will develop only by practice. That is the first thing, because same thing you can draw. If you are drawing, you will not get this kind of a very clear cut picture it's given in the textbook. Try to understand how they are drawing, and definitely this is a sure question, right? So in that time, whether they are asking you for 4-bit comparison or 6-bit comparison, accordingly you can draw it, right? So just understand how they are drawing, and I'm not forcing you to draw like this, but you can also try your own way. But finally it should look it should not look somewhat messy or complex. So the evaluator also, if somebody's university exam is coming, you should be able to give a clear picture of it. So let's see what is happening here. I mean the textbook, how they are explaining the concept. So what they done is like here, you will get a A3 complement, okay, and here you will get a B3 complement. And let me tell you what is the output. Some AND gate is coming, and what are all the input? Only input is like A3 complement, and another implement another input is like a B3. So here I am getting A3 complement and B3, and similarly here what you are getting, A3 is coming as it is and B3 complement. So it is something like XOR. You may be wondering why this XORs. Let's see. And finally this OR gate uh, with a bubble at the end. That is what. Hope you know this. This is your AND gate, right? And this is your OR gate with a negation. That is, NOR gate. Okay, fine. NOR gate. Negation OR. It will do the operation of the OR gate, and finally it will negate the result. So this NOR gate is giving me like the first input is this one and second is this one. So what it will take, A3 complement dot B3 or A3 B3 complement. So this is the output of OR, and finally I have a bubble at the end, means it is taking the complement of the whole thing. So this is nothing but, this the A bar B plus A B bar is your XOR, right? So A3 XOR B3 the whole complement. Let me write like this. So what is this? This is your XNOR operation. So that is your X3. Hope you remember. So you may be thinking, why I can use just directly this XNOR gate to do this. Fine, it is fine. But if you are doing that, you may be having some other difficulty when it comes to A greater than B, A less than B. And that case, here you can see that all these terms are like this is something you can see when you write this A3 XOR B3. What is it? A3 A bar B complement B3 plus A3 B3 complement. Actually, this is a subpart of this XOR gate, right? Similarly, you will find this A3 B3 complement here. This A3 B3 complement, this is actually this one, and similarly this is this one, like that. So if you are writing XOR, you will get a benefit that all this sub expression you can use for this A greater than B, A less than B cases also. Yeah, that's what I am trying to say. Is it clear? Try to understand that. Whether I make this diagram confusing for you, it's okay, right? So this is your X3. Similarly, they calculated X2, X1 and X0, and finally this AND gate is taking the input, that is all X0, X1, X2, X3, all of them are ANDed together. So this is a point where the output is like x3 dot x2 dot x1 dot x0, and this is going to give me a 1 when A equal to B. So first case is clear. Now for the second case onwards, you can take these sub expressions. So that is a benefit. For example, if it is A greater than B, the cases are like, you can see what is this. See this arrow, you observe, it's going like this and it's coming from here. So this is your first checking. So here this first input is actually coming like A3 B3 complement they are taking here. This one, you can see this, right? Similarly, now the second input, hope you remember the second expression, it is something like x3 dot A to B2 complement. A to B2 complement you will get somewhere from the second position, like I think this is actually your B2 complement, this is your A2, and from here you will get A2 B2 complement, and that is taken here, and this x2 is also, x3 is also taken here. So this is your x3, right? So this one is giving me as the output x3 dot this one, A2 B2 complement, and that I am taking and feeding to this one as a second input, the second term. Similarly, I am taking the third one, fourth one. Okay, so just observe the diagram. So this is there in your Morris Minor textbook. Anyway, I written something, I made it complex, but that is for the explanation purpose, and this will help you. I am not going to write much more into it. So in a systematic way, just try to, if you can draw like this, it's very good, because two benefits you will get for university exam, also for the next exam implementation. This is needed. That is why I am telling you. So try to practice drawing like this. Maybe in worst case, if you find it very difficult, you can draw in your own way. accordingly some final level, I mean mainly this equation matters, and whether you are able to implement this equations, the logic is here. It's finally something like whether you are getting your output or not. So like that, mark reduction may happen if you couldn't draw this diagram properly. So that is fine. If somebody is not okay with the diagram, it's okay. But anyways, this is the way they are drawing. Okay, fine. So just the three equations are implemented. That's all. Yeah, thanks for watching, and hope it is clear. It's actually so here you can see the uh, power of some logic like this. If you can observe that number, and if you can see something like this, these four case studies, and I observed this. Otherwise, I am having only the truth table method, which is very much what I can say, that many entries is a tedious thing. I don't want it, but this observation is making my circuit very easy, handy, right? So that is what is needed, not only for digital electronics, in any law, I mean data structure, algorithm, everywhere. This kind of a logical thinking is what is needed for a computer science student. So that is actually going to help you. So whenever you have a very confusing complex task in front of you, you may find something easier like this. So that is, if you can find it, it's okay. So that is what is needed, right? Yeah, that is where our, so how can you develop such a logical thinking? By exploring yourself to maximum such examples. So but that is a way I am suggesting, but some people are okay, fine, that IQ and all. But it depends. Even though when somebody's IQ is good, by practice only they can make it more sharpened, right? So yeah, that about it I was telling. Fine. Thanks for watching.